Hey everyone, it is Julie Beaver, and I am just looking through my project assignment and putting together some things that I'm really excited for my pre-calculus class. This is the 4th year that I'll have taught it, and so I feel a little bit more comfortable with the actual content to be able to go through and do some more problem solving with it. So I've picked 3 objectives from different places in the book, and so I'm going to kind of give you a main overview of one and then add in an extra bonus because I'm excited about it and it hits a little extra of the problem solving that the first does a little differently. So I was just really struck by a teacher of mathematics has a great opportunity. If she fills her allotted time with drilling her students in routine operations, she kills their interest, hampers their intellectual development, and misuses her opportunity. But if she challenges the curiosity of her students by setting them problems proportionate with their knowledge and helps them to solve their problems with stimulating questions, she may give them a taste for and some means of independent thinking from Polya. So I entered the sheet just because I was talking about myself, but the first problem-solving activity I picked for the second lesson of the year. And it's basically just looking at a coordinate plane, the Cartesian coordinate plane. And so this is something that the students should know. They started looking at graphs back in elementary school. I know that they started absolute value in 7th grade. They could find the distance between 2 points in 8th grade. They could find the midpoint of a segment, 7th grade, 8th grade, and following. And so this is review content, and so I don't want to stand up at the front of my class and lecture them on how to do these things when they should already know them. And that has not been successful for me for the last couple of years. But I did one year try to skip it, and that did not work either. They actually need to review the content. So how can I do that in a more open-ended way? So here is my plan. I'm just going to give them this picture right here. So it's a Cartesian coordinate plane and it has 4 points on it. And my students are sitting in groups of 4. So there's 4 desks put together. And usually I have 3 to 4 kids set there. Now it's the beginning of the year. So at this point in time, I might still have them just allowing them to sit by friends. But in general, they will be heterogeneous groups. So I will just give them this picture and say, given this information, what questions would a mathematician ask? I'm asking this early in the year because this right here is a question that I want the students to ask themselves over and over and over again. So I want to put that language into their heads right away. So given this information, what questions would a mathematician ask? And then over here I have a timer. Because if I don't set a timer, I have no concept of time. So I will say for 2 minutes, you're going to brainstorm with a piece of paper individually. I think it's very important to have that individual time. Kind of like when we did our problem set 4 or 5 when we did the group piece on A5. And we had to work by ourselves for an hour first, and then we went to the group. Well, a student needs to be able to think through these things by themselves first for several reasons. Number 1, I want their brain working. Number 2, oftentimes you'll have one person who kind of takes over the group or one person who says, oh, I'll let them think of it. I want them all to be brainstorming on their own first. Then we're going to go with a 4-minute group, come up with a list with your whole group. So every person has something to offer. I might give them a little structure. One person shares something, then the next person, then the next person. We're going to come up with a group list. Then I'm going to pull the kids back as a class, and I have one side of my room has a whiteboard across the whole side of the room. So I'm going to have 2 kids with whiteboard markers, and we're going to make an exhaustive list. So my plan for getting this exhaustive list is to start with one group, and they have to share one thing, and then go to the next group, they share a different thing, next group, they share a different thing, and then we just keep going around the groups And each time a different person has to talk until we have as many questions as we can think of that go with this picture right here. And there's all sorts of questions. You can figure out length. What is the length between C and D? What's the length between C and B? So you have distance formula. You have counting. You could do ordered pairs. You could talk about what quadrant is this in. Are A and D even on a quadrant? All sorts of things. So at this point in time, we're just looking for questions. We're not looking for solutions. But my whole goal is that the students would be able to figure out all of the questions and be able to list all of the things that they know about this, because they know a lot. So after we've come up with an exhaustive list, then I would put up my objective and my sub-objectives on there just to make sure that we've covered everything. Now, I would have a list of my own already made to make sure that we've covered everything I want to cover. But then I was thinking to myself, well, wouldn't I want the students to do that? So if I then gave them what we're trying to cover and what I really want reviewed right now, I could say, okay, do we have things about I know and can use the Cartesian coordinate plane vocabulary? We covered all the vocabulary questions. And if we haven't, we can add some more. Then I can plot data on the Cartesian coordinate plane. Well, they hopefully talked about ordered pairs, but then maybe they could add in another question about that. Absolute value. How does absolute value even fit in on there? Do we have absolute value questions? Well, absolute value comes into the distance, so maybe we need to add more questions. Can I find the distance between 2 points? Hopefully they've asked something there. And can I find the midpoint of a segment? They might not have thought of that. But if I bring it up, then we can add it. So then, once this list is made, I will take a picture of it and post it to my Schoology page. So our school district is 1-to-1. Each kid has a Chromebook, and we have a learning management system online. It's like D2L, just called Schoology. So that then the student's job will be to find solutions to all of those questions. Now, given, I don't know if that's 200 questions that we've come up with, my teacher heart would be so excited. I then will monitor and adjust according to the amount of questions brainstormed, because I've never done this before, so I don't know exactly what that's going to end up looking like. But just even the kids thinking about the original questions, they've probably answered them in their head already, so we can go after maybe some of the more challenging ones. As I was looking through writing for my project and going back and making sure I was covering every module, I went back to Margaret Taplin and what is a problem-solving approach. And I really liked the interactions between students and teacher and students. This covers that. Mathematical dialogue and consensus between students? Yes. Teachers providing just enough information to establish background intent of the problem? Yes. Now, one of the things, is this necessarily problem, like having a problem and solving it? No, it's more problem posing from Module 5 in this one. But I think all of that is valid and important, and so teachers guiding, coaching, and asking insightful questions, yep, we have that. And right here, teachers knowing when it's appropriate to intervene and when to step back, and students make their own way. That's what I want to do. That's my whole point. I want to give this to the kids, especially at the beginning of the year, so they get used to that, because if I don't do it until November, I won't do it. Minimum level of mastery. In general, I want students, pre-calculus, it's a college class. Most of the kids are a year ahead kind of in our course pattern, so they should be getting 80% on an assessment. And this content, they should be getting it all right. So this could be a quiz, it could be a test. This year, I think that I'm going to give the in-class part of the test, and then I'm going to implement problem sets like we've had each module, because I think that's amazing. So that kind of, in an assessment point, that's the minimum level of mastery that I want. In the exercise itself, I just want kids thinking about the questions and things that they should be able to solve. Aspirational goals, that the students would come up with deeper questions, not just the superficial ones of what quadrant is it in, what's the distance from here. So an example of that would be, where could we place a new point so that if you connected it with another point, it would make a line parallel to a line connecting two other points? That's way too many words, but finding parallel, perpendicular, that would be awesome. So that's what I'm looking at for my first problem. But then I'm just really excited about my second one, which is the next week. And we're just reviewing quadratics and looking at projectile motion, which even though students have covered projectile motion a whole bunch, they don't necessarily make all the connections or remember how it works. So my plan is to show a video and then just asking them, after seeing this video, what questions would a mathematician ask? And then what kind of specific information would they need to answer these questions? Because I'm not giving them any information at this point in time except for, hey, this super cool rocket just shot off. So I'll give them the 2 minutes and the 4 minutes, so 2 minutes individually, 4 minutes as a team. And then I'll give them some actual information. So a projectile is launched straight up from the ground with an initial velocity of 256 feet per second. What questions would a mathematician ask, and what strategies would they use to solve these problems? So I will let them ponder that for a while. Then, after a little bit of time, then I will throw in there, what if I gave you the number 768 feet? What other questions could you ask? So the original question from the book says, when will the rocket be below 768 feet? When will the rocket equal 768 feet? And when will the rocket be above 768 feet? Which is all fine and good, but the kids could come up with other questions or questions that actually interest them. And so I want them to be the problem posers. So after that, then I would have them again solve the problems that they have. Now, one of the things they'll say is, we need a formula. Yep, and I'm not going to give you the formula, but you do have Chromebooks, and so we have some tools. What tools do you think you could use to find the formula? Something that I think that will be interesting, and this goes into my above and beyond. Again, I'd want students to come back at this point in time that they would be able to answer the simple questions. What would be the maximum? When would it hit the ground? Those are questions that we would probably ask. In an assessment setting, I would want them to be at 80%. But then the above and beyond piece, my aspirations, well, as I'm thinking about that, I would want some of them to have a dilemma of, how come this one formula is negative 9.8 and this other formula uses negative 16? Why do they use different things? I'm almost positive kids would come up with different answers because scientists generally work in metric, but in pre-calc, for whatever reason, we use the negative 16 or feet per second. And so just all of these different, why would we do it differently? And just going through the questions like that and making sense of the world and different measurement systems. So there's my problem solving thinking, all in 14 minutes.